Hey guys, Mrs. Melcher here, just to give you some examples and prep on what to do in section 12.2 from your book, Chemistry, Matter, and Change. I decided to go over this lesson with you on YouTube so that if you're lost and you don't know what you're talking about in the book, you'll have some good examples on what to do. Now, if you have questions, you should write them down. You can either write them in the comments, which I can check, otherwise you can write them down on a piece of paper and ask them when you get back. And I'm going to be doing it on PowerPoint because it'll be more easy to see for you if you want to take some notes, and then you won't have to read my scrawly handwriting. I'll do some examples on the board while we're going through it, and hopefully you'll be able to understand this section. All right, let's get started. Okay, so we've already talked about section 12.1. Now this is 12.2 called Stoichiometric calculations. If you remember, stoichiometry is just the study of how things go from one state of matter, potentially the reactants, to the products and their ratios, how things change and whatnot. So a review, you can use a mole ratio if you know something of one thing, but you do not know the amount of something else. So we're going to go through some dimensional analysis today using stoichiometry in order to calculate the different ratios and numbers to find your answer. I'm on my stool, so give me a minute. All right, I'm just going to talk over here and hopefully you'll be able to follow along until I show you the example. The first thing is, say we have 2.8 moles of iron. The question is, how many moles of iron 3 oxide are there if you have 2.8 moles of iron? So this is similar to some of the things that we've been doing in the past, but it's a little bit different. The first thing that you need to do is figure out the balanced equation. So here we have an equation. It is not balanced, however, but you'll note that it does state the states of matter. Number 1, balance the equation. I've got iron plus oxide, noting that the oxide is O2, and it's going into my Fe2O3, also known as iron 3 oxide. Here's the balanced equation. I've balanced for the iron and the oxygen, keeping in mind the subscripts, and putting the 4 and the 3 beforehand as the coefficients. Once the equation is balanced, then you'll be able to use it to determine the stoichiometric ratios. We've talked about the ratios before, and you can see what the ratios are here. We have 4 iron to 3 oxygen, 4 iron to 2 iron 3 oxide, 3 oxygen to 4 iron, 3 oxygen to 2 iron 3 oxide, and so on and so forth. So for this specific example, I know iron, but I'm wondering about the iron 3 oxide. So the most important ratio that we're going to be using here is the iron to iron 3 oxide, which is iron 4, iron 3 oxide is 2, so it's going to be the 4 to 2 ratio. Alright, I have plugged it in here just easily on my PowerPoint, but I can show you how to walk it through here. The first important thing is that I put the 2.8, which remember, like I say, is always use what you know. So the 2.8 is what I know from the equation. There are 2.8 moles of iron. That's what I know, 2.8 moles of iron. And what you'll do in this dimensional analysis stoichiometric calculation is just like we've always done. Take the one that you already know, put it down here in order to be canceled out, and put the one that you're looking for up here. So we've got our 2.8 moles of iron, and I'm using my mole ratio, which, like I said before, was 4 to 2. So the one that I have, I can cancel it out on the bottom by crossing out the iron, and then on top, because there's 4 moles every 2 moles, I'm left with the iron 3 oxide just like I wanted. So if I do this with my calculator and plug it in, it's going to be the 2.8 times 2 divided by 4 in order to give me my stoichiometric calculation on how many moles there are of the iron 3 oxide. If you do plug it into your calculator, 2.8 times 2 divided by the 4, And just note that I have it set up here differently than we've had it set up in the past. You can put the line here, that's how I was taught, but you can always put the multiplying sign here like we've been using most of the time in class. The answer would be 1.4 moles of iron trioxide, and that's just because of the ratio. You'll multiply what you had started with the molar ratio. Again, if you have any questions or comments, you should write them down at this time. All right, I'm going to move on to another example. And this example has an extra step to it because we're not only going to moles like we did in the last problem where we started with moles and we went to moles, but in this problem we're going to be starting with moles and going to mass. So that means starting with the moles and going to grams. Here is an example problem. You can write it down if you want. Feel free to pause at any time if you need to write down the problem. But I think this problem can also be found in your text if you take a look at that. So here we go. Determine the mass of sodium chloride produced when 1.25 moles of chlorine gas reacts vigorously with sodium. All right, step one is going to be to write a balanced equation. I'm going to pop this screen up so that I can show you how to write the balanced equation for this. And let's see. Okay, so I know you can't see it very well, but here I can pull it down while I'm writing. Determine the mass of sodium chloride produced. So I know that that's going to be in the products because it's specifically telling me that it's the sodium chloride produced when you have 1.25 moles of chlorine gas reacting with sodium. So I'll start out with my sodium. You can start with your chlorine, doesn't matter. And if I look on the periodic table, I can tell that sodium is a solid. And it's going to react with chlorine gas. Remember that chlorine is part of the Bill Nye element, so it always travels with its friend, and that's a gas. It's going to be reacting vigorously together to produce sodium chloride, which is a solid, but could also be an aqueous if it's in solution, which this might be in solution, but we'll just say it's solid for now. Okay. So I did that. I wrote an equation, but I did not balance. So I'll balance it. See if you can figure out how to balance it before I balance it here in just this one moment. I have my two chlorines, so I'm going to put the 2 over here, and then I have my 2 NA, so I'm going to put the 2 there. First step completed. Balanced equation. Okay, write the mole ratios and determine the one that is needed. So we'll be able to write as many ratios as needed here. We've got our 2 Na for every 1 Cl, 2. And then we've got our 2 moles of Na for every 2 moles. I just wrote moles there. I guess you can write moles on everywhere. That's probably what we should do. NaCl. We've got 1 mole of Cl2 for every 2 NaCl. We have 1 Cl2 for every 2 Na. We have 2 NaCl for every 1 Cl2. And then we have 2 NaCl for every 2 Na. All right, determine the one that's needed. Well, I'm trying to determine the mass of the sodium chloride from the chlorine gas. So my problem is starting with 1.25 moles of chlorine gas. 1.25 moles of chlorine gas. I find it easy to write down what I'm starting with above the equation and then put a question mark about what am I trying to find. I'm looking actually here for grams, so I'm going to start with my moles and move to grams. If you don't write above what you're looking for, it's easy to get confused along the way. By using this method, I can easily pick out which mole ratio I need, and that's going to be the chlorine to the NaCl. So that one is right here. Multiply the number of moles by the mole ratio. So to start with what I have, which is the 1.25 moles of chlorine. And we'll just do some dimensional analysis here. We've got the chlorine, it says chlorine here. So 1 mole of Cl2, and I'm trying to find my NaCl. 1 mole of chlorine, according to this, equals 2 moles of NaCl. That's some easy math. Just do the 1.25 times 2 equals 2.5 moles of NaCl. If you have any questions, feel free to write them down now. Okay, last step in converting moles to mass is to convert the moles of chlorine to grams. So you already know how to do this. We've been doing this for the last 2 chapters now. Take your 2.5 moles of, actually this isn't even right because, oh yes, this is right. Convert the moles of chlorine, 2 grams. So we've already found the moles of chlorine and we've converted it to NaCl. So ignore that. 2.5 moles of NaCl. And now we can multiply by the molar mass. So if you look up the molar mass, we've got 23 for the Na plus our 35.5 for the Cl. We're just going to go some molar mass of 58.5 grams per mole. So if I'm doing my dimensional analysis like I've been doing this whole way, 2.5 moles of NaCl. And you can look on your blue sheet as a reference too. For every 1 mole of NaCl, there's going to be 58.5 grams of that. So we'll just do the 2.5 times the 58.5. I grab my calculator. I can calculate that. You can also be calculating along with me while you're watching this video. That would probably be an excellent idea. 2.5 times 58.5 equals 146.25 grams of NaCl. Okay, now just to recap what we did with this question is actually we did it quite a lot. We started knowing how many moles of chlorine and we finished learning how many grams of sodium chloride are produced. Now you might be asking yourself, why do I need this? Well, if you were in the lab, or if you know anybody that works in a lab, or if you like to consume food, or if you use medicine and other types of drugs, then scientists use this to figure out how much they need to start with, how much reactants, in order to make the products they need. So let's say a scientist wanted to find whatever 500 grams of sodium chloride, or even 500 grams of acetaminophen, which is Tylenol, or 100 grams salicylic acid, which is aspirin. Then they need to know how much products to put in to try to get their reactants. All right. We can go over another example as needed. If you understand, you can feel free to stop the video and continue on with the rest of your life. But if you would like one other problem to help you get through, then I'll also walk you through this problem. Okay, we've got ammonium nitrate. If you don't know what that is, you might want to reference your periodic table on the back side. Ammonium nitrate produces NO2 gas, so dinitrogen oxide gas, dinitrogen monoxide, gas, and water when it decomposes. Determine the mass of the water produced from the decomposition of 25 grams of solid ammonium nitrate. All right, a lot of steps in this problem. So we're starting with something that's decomposing. We've got a decomposition reaction here. Ammonium nitrate. Remember the charge here is minus, it's plus, so when they crisscross, they just cancel out. Ammonium nitrate is going to decompose and produce N2O plus H2O. Do you remember what the first step is? Balancing the equation. I think it'll say if I click through it too. Step 1, write a balanced chemical equation. Okay, so I already have my equation, now I'm going to balance it. Let's see, I've got my 2 N's here, and I've got 2 N's here. H's, there are 4, and there I have only 2. But I see the tricky part already, and that's the oxygen. So if you want to get ahead of the game, A good thing would be to balance this oxygen right away, or even to multiply by 2. That's my special trick, is I always multiply by 2, so that I can multiply it up later as needed. All right, now I have 6 oxygens. The hydrogens, I'm at 2 times 4 equals 8, so I'm just going to automatically put a 4 here to balance. And then let's see where we're at with our oxygens. We've got 4 here plus 5. And now if I know that if I put a 2 here, then I'll be where I'm at for the oxygens. I've got 2 plus 4 is 6. I have 2 times 3 is 6 here. I have 2 and 2 is 4 nitrogens. And I've got 4 over here. I've got my 4 times 2 hydrogens, and I have 4 times 2 hydrogens, so 8 hydrogens. All right, that was a little bit of a tricky problem to balance. So for now that I'm looking at it, I see that I can simplify it. So I'm just going to erase that one, and then erase this one down to a 2. Let me count this up. 1, 2, 3, 1, 2, 3. I guess that was easier to balance than my original thought. Sorry if that was confusing to you. I'm not going back and remaking this video. All right, convert grams of the ammonium nitrate to moles. So we're starting with what we know. Like I said before, you can always write what you know above it. I'm starting with the 25 grams of this. And I'm looking for the mass of the water, which is how many grams of water produced. Convert mass of that to moles. Okay, 25 grams of the NH4NO3. And then we'll have to determine the molar mass to figure out how many is in 1 mole. Got my handy calculator here, so I can calculate. You can calculate along with me. I've got 28 plus 4 plus 3 times 16. So 80 grams are in 1 mole. So we'll just do a little bit of multiplication, or division rather, here. 0.3125 moles of the NH4NO3. I know you can't see this very well with the string in the way. All right, the next step is going to be a mole-to-mole ratio. And then we're going to multiply and convert to grams. I just popped through this so that I can write it without having to move to a different location. I'll switch colors for ease. Hopefully you'll be able to tell the color switch. The mole ratio. So I'm looking for the water, and I'm starting with the moles of the ammonium nitrate. So I'll just write ammonium nitrate. I've got the 1 NH4NO3 for every 2H2O. Okay, multiply the mole by the mole. We've got 0.3125 moles of the NH4NO3. And check your mole ratio. For every 1 of this, I have 2 of that, so 1 goes on bottom, 2H2O goes on top. I'm going to multiply that by 2.3125 times 2 equals 0.625 moles of water. And last step, convert moles of that to grams. So I have, this should not even say this, it should say water. So I've got this, 625 moles of water. And if you remember how many grams are in a mole of water, which I think I do right now, it's 18 grams. So we can cancel that as per usual. And that's a multiplication problem. The answer is 11.85 grams of water. All right. That is the lesson and examples for this section. If you're confused, you can, again, write down any questions or go back and read through the text, section 12.2. Hopefully this video has been informational for you. Let me know when you get back from your trip. And please bring me something, like an apple from the Big Apple. See you soon!